Okay, so you want to start a minute early, or do you want to wait 1 minute?
I'll wait a minute.
Okay, cool.
Yeah, people are still in the discussion room. Gian, in the meantime, let me catch up. No recording yet. Just
Thanks for inviting me.
Do you want me to introduce you, Trithep?
Oh yeah, sure.
People can't read. Okay, go. We have a great session for the next hour and so a bit. And the first speaker is Trithep Devakul, who's going to tell us about fractal phases of matter and fractalization. Take it away, thanks.
All right, so I'm going to tell you about this weird thing called fractalization, which is it's going to be part of an upcoming paper with Dom. So let me just get started. So the outline of my talk is, well, let me first tell you what fractalization is. It's a recipe for extending certain spin models, say from D dimension to higher dimension. And this recipe takes as input fractal, which is which is specified by some linear cellular automaton rule. And I'll tell you what this is. And sort of the upshot of this is that it allows us to connect various exotic fractal models with more conventional models. For example, we have some fractal symmetric Ising model, which is an Ising model, but has some fractal symmetry. And this is through fractalization, this connects to just a standard Ising model. You have SBT phases that are protected by fractal subsystem symmetries, and these are connected to just the cluster state. You have these type 2 fracton models where sort of the logical operators are these big, complicated fractal operators, and these are connected to just the standard Toric code. And I'll go through all these examples in this talk. So first, I'm just going to introduce some ideas, cellular automata, fractals, polynomials, and how they're all connected. Then I'll define what the fractalization procedure actually is. Then I'll give you some examples, the 3 examples I mentioned earlier. And then I'll talk about some applications. So one of which is a coupled layer construction of type 2 fracton phases, and another is a fractal version of the Bacon-Shor subsystem code, which we conjecture to saturate some information storage bound. Okay, so let me just introduce linear cellular automata, or LCA. So each cell of an LCA is in either on or off, 0 or 1. And say this is a one-dimensional LCA. The state is determined by some string of 1s and 0s, which I'm going to draw as a picture of black and white dots. And it comes equipped with an update rule. So the state at some time t is determined just by the state at some time t minus 1. And I'm going to focus on the case where this f function here is some linear, local, and translation invariant function. So that means that a of it can be written as some sum over j of some f I minus j, and then the state at time t minus 1 mod 2. So all arithmetic is mod 2. So as an example, we have the Wolfram's rule 60 denoted pictorially here. But what this means is it just means that the state at time it is equal to the state at time I t minus 1 plus I minus 1 t minus 1 mod 2. So you can see 0, 0 gives 0, 0, 1 gives 1, 1, 0 gives 1, 1, 1 gives 0. So you start off with some state at time 0 here, go up to state at time 1. You just make sure that everything is consistent with these rules, and that'll give you some time evolution of a LCA. And the neat thing about linear cellular automata, or why I focus on linear ones in particular, is because, so let's just look at this rule 60 example again. Suppose we start off with a state that's just 1 at one point and then 0 everywhere else. And then you just evolve this forward in time, which is downwards in this graph. You end up generating this Sierpinski triangle fractal, and you keep going, it'll keep giving you this structure. And it's not a coincidence that this is a fractal because, well, all non-trivial LCA rules result in some fractal structure. The fractal might be different, but it'll always be fractal. And this follows from just an algebraic property of polynomials. So to see that, we can represent a state at time t, so the set of all AIT for all i's. You represent that as a polynomial, a of t of some variable x, where each monomial x to the I is just, the coefficient is just 0 or 1, depending on the state at cell I. Your rule, your update rule, used to be determined by this function f, now is just also determined by a polynomial. And the update, which used to be this formula, is now just polynomial multiplication with coefficients in mod 2. So you can specify an LCA root just by a single polynomial f of x. And so again, coming back to this rule 60, you have f of x equals to 1 plus x. And so if you start off with some polynomial some state a naught of x, and then you evolve to some time t, this is just equivalent to multiplying by f of x raised to the tth power. And if you look at what this looks like, f of x is 0 is 1, f of x is 1 plus x, f of x squared is 1. The coefficient of x here is 2, which is equivalent to 0, and then x squared. And so if you keep going, you find out that this structure here is exactly this Sierpinski triangle. And the property of F2 polynomials is that if you raise some polynomial to the 2 to the nth power, this is equivalent to the same polynomial of x raised to the 2 to the n. So this guarantees that you always have some fractal structure, some recurring structure at every t that's a large power of 2. Okay, so let me now connect this to spin models. So let's just consider a spin model that enforces on its ground state a valid LCA trajectory, space-time trajectory. So we map sort of state 0 and state 1 to the z state of spins, plus 1 or minus 1. And you just have a Hamiltonian that looks like this. And this just enforces that every 3 spin in this configuration has to be one of these 4 configurations. So now any valid LCA space-time trajectory is a valid ground state of this Hamiltonian. So for example, this fractal would be a ground state. And this Hamiltonian is actually studied a while back by Newman and Moore. So I'm going to call it the Newman-Moore model. And so due to the linearity of the update rule, you can sort of see from this picture that it's just linear. So flipping any set of spins that corresponds to a valid space-time trajectory gives you another ground state. So for example, you're supposed to start with this ground state, then you flip all the spins. So you act on the ground state with a product of Pauli x's that flips the z state of all the spins, but it acts on sort of this set of spins. You end up with a state that looks like this. This is another ground state of your Hamiltonian, and so this actually commutes with the whole Hamiltonian, and so this is what I mean by a fractal subsystem symmetry. Now, what I'm going to tell you is that this Newman-Moore model, which exists in 2D, is actually related to the 1D Ising chain by this fractalization process. So if you put the Ising chain vertically, it has ZZ couplings on nearest neighbors. Through fractalization, this becomes this 3-body ZZZ coupling. You have the global symmetry of the Ising model, which is a product of x's on all sites along the chain. And this becomes this fractal subsystem symmetry of the Newman-Moore model. Okay, so to properly define this map, I sort of need to use a polynomial representation for Pauli operators. So let me just quickly go through that. So in 2D, you can represent Pauli operators, sort of x's and z Pauli operators, by a function from a polynomial to the Pauli group. So x of some polynomial, Cij, x raised to the x to the I, y to the j. For each coefficient of Cij that's non-zero, this just corresponds to a factor in the product xij, and similarly for z. And fractalization is just, so there's sort of the cookbook. You have some operator, say it's a pure x operator, it's just x of some polynomial a of y. To get the fractal operator, you just replace y by f of x times y. Similarly for z operators. And sort of I'll go through many examples of this later. So this is just a definition, and you can generalize it to be a mapping from any d to d plus m dimensions. Now there's also an alternate view of, so this is sort of the mechanical way to do it. You can just take a model and do this. You can also view it as a different process, which is if you have some set of operators, A, which has to be pure X or pure Z operators, and you map it onto some set, the fractalized version. This is actually equivalent to starting with the same operators, but in a layered system. So you just take layers of your original system with R parallel and R perp. And then you make a non-local choice of generators along R perp. So you define A tilde, which is some non-local product of A's along the perpendicular direction. And then you follow it up with some non-local unitary transformation, which sort of restores locality to these generators. And so this view will be useful later on when we're talking about the subsystem code. But let me just summarize. So fractalization is this process where if you're given a pure X or pure Z type operator, Pauli operator in D dimensions, it'll extend it to some operator in D plus M dimensions. And some properties that this satisfies are local operators always map to local operators. Non-local operators like symmetries or logical operators tend to map onto operators with fractal support. And this mapping preserves commutativity. So if A and B commute, then their fractal versions also in higher dimension also commute. So what this means is that if you have a CSS code, it maps onto another CSS code. If your model has some global symmetry, it maps onto some fractal subsystem symmetry. You have non-local logical operators, it maps onto a fractal logical operators, and also many other properties are similar to having stacks of the original model, as I'll show you with some examples. So first, let's look at the Ising model. I spoiled to you that the Ising model is related to the Newman-Moore model. So if you write down the polynomial representation of the Ising model, it's just C1 plus Y bar, where Y bar is just sort of Y inverse. And I've written it in this way so that you can just plug it into the fractalization cookbook. You end up with this model. And if you write down the terms, you find that it's exactly the Newman-Moore model. You have your fractals, you have your global symmetry of the Ising model. This is just sum over all powers of Y, which means product of X over all sites. When you go through this fractalization, you end up with an operator that looks like this, where recall that F raised to the nth power is really the nth time step of this cellular automaton. So this will look like, will give you an operator that looks like this fractal that's generated by the function f of x, which in this case is just 1 plus x. Another example, let's look at the 1D cluster model. So the fractalization requires sort of a CSS form. So every operator has to be of X type or Z type. So if we write the cluster chain in the CSS form, which looks like this, so there's a chain, you have to group two sites to be part of a single unit cell. And you have two terms in the Hamiltonian, which is an XXX term or a ZZZ term, and they all commute with each other. You can write this in polynomial form, it looks like this. And now we go through fractalization using this, the same LCA rule that we've been using. You end up with the Hamiltonian that looks like this. So the XXX term here becomes XXX, but then there's now an extra X up here. And the ZZZ term becomes this ZZZ, but then there's now an extra Z down there. And if I sort of draw lines connecting these layers together, you find that this is another cluster model, and it's on a lattice that is isomorphic to the honeycomb lattice. So this is the honeycomb lattice cluster model. And if we look at what the symmetry does, so the cluster chain has this global Z2 symmetry, which is Z on every even site or X on every odd site. This commutes with the Hamiltonian. You go through fractalization, and you find that this X operator maps onto some to an operator that has the support of the Sierpinski triangle. Perhaps it's best clearly seen if I put it on a honeycomb lattice. So this is the same model as before. You have product of Z's on all these downward facing triangles, so Z, Z, C, Z, and product of X's on all these upward facing triangles. And every term commutes to each other. And if you look at the symmetry of this Hamiltonian, it's either a product of Z's on all these blue sites, so it's a big Sierpinski triangle, or a product of X's on all these red sites, so it's like an inverted Sierpinski triangle. And so sort of many properties of the honeycomb cluster model is similar to that of the cluster chain. For example, let me just summarize. So the global symmetry of the cluster chain mapped onto the fractal subsystem symmetry of the honeycomb lattice model. The cluster chain is a non-trivial 1D SPT. The honeycomb lattice cluster model is a non-trivial 2D fractal subsystem SPT. Some of you might know that the cluster chain, there's a non-local mapping that maps it onto 2 copies of symmetry-broken Ising chains. Similarly, for the honeycomb lattice cluster model, there's some non-local mapping that you can do to map it to 2 copies of the Newman-Moore model, which is just the fractalized Ising chain. There's a string order parameter for the SPT phase of the cluster chain, and similarly, there's a fractal order parameter for the subsystem SPT phase of the honeycomb lattice cluster model. They're both unstable to finite temperature, and measurement-based quantum computation is possible using both of these phases. Another example, Toric code. So in 2D, fractalization actually takes 2 LCA rules as input, f and g. So let me just use the same f as before, but now g is some other polynomial. Let me just use 1 plus z squared. You start off with the Toric code. The stabilizer is a product of x's on crosses. So it's on the cubic, on the square lattice with cubic degrees of freedom on the bonds. The stabilizers are product of x's on all crosses or product of z's around a plaquette. You write it in polynomial form like this. You go through fractalization, you end up with a Hamiltonian that looks like this. If you draw it out, you find that there's the x term looks like an x across an x on this cross, but then it sort of spreads out in the z direction. The z term looks like the plaquette term from before, but then it spreads out a bit in the z direction. And this is a complicated looking Hamiltonian if you draw it like this, but it's really simple in the polynomial representation. And this is actually Yoshida's fractal spin liquid Hamiltonian, which is an example of a fracton topological order. So if you look at, say, the x string logical operator of the Toric code, which is product of x's along this line, it commutes the Hamiltonian. It's a logical operator. You find out what this maps onto in the fractal spin liquid. It maps onto this operator, which is just a product of x's along this line, but then it spreads out in the z direction. And the way it spreads out is according to this Sierpinski triangle. So on the red bonds here, if you look, you see that this is a triangle, this is a triangle, this is a triangle, and you keep on going. And it'll generate this fractal. And you can also shift this along this z direction. So there's actually LZ independent fractal logical operators. So to summarize the Toric code, Toric code has some non-trivial topological order. This fractal spin liquid has some non-trivial fractal topological order. The string logical operators of the Toric code map onto fractal logical operators in the fractal spin liquid. Ground state degeneracy of Toric code is 4 on a torus. If you put the fractal spin liquid on a 3 torus, ground state degeneracy will scale roughly as 4 to the L. They're both unstable to finite temperatures. So one way of obtaining the Toric code is as sort of through this gauging map, or this Kramer's Wannier map that Nat talked about in the first day. You can get the Toric code from gauging the global symmetry of the 2D Ising model. Similarly, you can get the fractal spin liquid from gauging some fractal symmetry of some Ising model. And what Ising model is it? It's exactly the fractalized Ising model, 2D Ising model. And this is also not the usual gauging procedure. This is this generalized gauging procedure. Okay, so these were some examples. Let me talk about the first application, which is coupled cluster state construction of these type 2 fractal phases. So let me just show that it's possible to construct Toric code from coupled cluster state wires. So, and then we're going to use this information in the next slide. So suppose we start out with this cluster chains that are sort of in arrays vertically and horizontally, where now I'm taking it to be sort of X, and the cluster chain Hamiltonian is X on a site and the product of Z's on all of its neighbors. And then what I want to do is I want to look at all of these pairs of sites that are overlapping each other. And I'm going to add a strong ZZ and XX coupling term to them. Now, if I turn this ZZ coupling up to infinity, you find that at the low energy physics described by, just do perturbation theory, you find that this Hamiltonian just becomes the cluster state on this sort of decorated square lattice with qubits on both sites and bonds. And there's an X field on the qubits that sit at the sites of this square lattice, sorry. Now, if you take the XX coupling to infinity as well, and these two limits commute because XX and ZZ commute. So you take this limit, and this Hamiltonian just reduces to Toric code in the low energy limit. So now we can just apply fractalization to this whole procedure. So a fractalization to each of these cluster chains becomes a fractal cluster state. For example, this would be a stack of honeycomb lattice cluster models sort of in the XZ and the YZ directions. And you again add an on-site ZZ and XX coupling term, you turn up the strength to infinity, and what you'll end up with is Yoshida's fractal spin liquid Hamiltonian. So this is a way to obtain these complicated models by coupling two-dimensional cluster state layers. And sort of in our upcoming paper, we sort of have more general coupled layer and wire constructions of other fractal phases, including Haas code. Let me now talk about another application. So the Fractal Bacon-Shor subsystem code. So let me just briefly review the Bacon-Shor code. So the subsystem code, the Hilbert space, has this structure, which is, it has some logical subsystem. So it's separated into two subspaces, so this error subspace, and then you have this code space, which further has a subsystem structure. There's H logical and an H gauge. So, and H logical will contain logical information. H gauge is just some other gauge degrees freedom that we don't really care about. So the Bacon-Shor subsystem code has this locally generated gauge group, which is the product of X's on two sites that are along the X direction, or along with the product of Z's along two sites that are in the Y direction. And so from this, you can determine the stabilizer group, which is, in this case, is the product of X's along two any two columns, or the product of z's along any two rows. And you can also determine the logical operators. So there's bare logical operators, which is the product of x's along one column, or the product of z's along one row. And you also have these dressed logical operators, which is the product of a bare logical operator and some element of the gauge group. And the way that these logical operators act is sort of the bare logical operators will act only in this logical subsystem, along with ignoring whatever it does in the error subspace. It will act in some way here. Gauge group will act only in this gauge subsystem, and sort of dressed logical operators will act sort of in both. And this code protects one logical qubit. And the sort of the Pauli algebra on this logical qubit is generated by these. You can see that these bare logical operators, they generate the Pauli algebra on this one logical qubit. So let me just apply fractalization to these two generators. So the ZZ term becomes this ZZ term in 3 dimensions. So there's ZZ, but then now it sort of spreads out a bit in the 3rd dimension. The XX term becomes XX, but then it now spreads out a bit in the Z direction. So now what do the stabilizers look like? So the Z stabilizer used to be a product of Z's along 2 rows. Now it becomes a product of Z's along 2 planes, but there's some structure within each plane. So it's sort of in this plane, you have this Sierpinski triangle. Sort of in the next plane, you have some other fractal. And this, you just follow the cookbook definition using these gauge generators. You find out these are the stabilizers. The logical operators are just going from a Z in one row, they become Z's along a fractal structure within one plane. And similarly for the X stabilizers and logical operators, you can, those will be along columns and they'll just be planes. And each translation along the Z direction gives you an independent logical operator. And so you will end up with sort of LZ logical qubits in this model. Okay, so let me just talk about the information storage capacity of this code. So this NKD notation, so I'll denote a code by NKD. If it has n physical qubits, it protects k logical qubits, and there's a code distance d. So for subsystem code, the code distance is the minimum of all the dressed logical operators, the weight of the minimum weight of the dressed logical operators. So for the Bacon-Shor code on the L by L square, we had L squared qubits. It protected a single logical qubit, and the code distance is just the weight of this logical operator, which is the product of X or Z's along a line, and so that has weight L. The fractal Bacon-Shor code, on the other hand, on an L by L cube, has L to the 3rd physical qubits. It protects L logical qubits, and the code distance we assume goes as L to some power eta, and so eta is bounded between 1 and sort of the fractal dimension of the logical bare logical operator, which in this case is around 1.58. And it's difficult to prove to find exactly what this is, because it involves sort of this minimization over all dressed logical operators, which is a difficult thing to actually do. And in D dimensions, there's some fundamental bounds on what these parameters, NKD parameters of a subsystem code can be. So this distance is upper bounded by the n raised to some power. And there's also a combination of k and d that's upper bounded by n. So let's see where our codes sort of stand in this bound. So Bacon-Shor code in 2D, d is equal to L, which is upper bounded by order L, so that's good. But KD is equal to L, but it's upper bounded by L squared. So there's some room for improvement here. Namely, we can increase K by another factor of L. If we look at our fractal Bacon-Shor code in 3D with these parameters, the distance is L to the eta, which is less than L squared, since eta is bounded between 1 and 1.58. And in 3D now, the combination that matters is K to the K times square root of D, which is scales as L to the 1 plus eta over 2, which is between L to the 1.5 to 1.79. And that's obviously less than L to the cubed, but it's still far from saturating the bound. So how do we improve this information storage capacity? Well, in 2D, what Bravyi has a generalization of the Bacon-Shor code that saturates this 2D bound. So let's just take that and apply fractalization to it and see what happens. So Bravyi's generalization is as follows. So you just take the Bacon-Shor code, but then you remove some sites based on some binary matrix Aij. So if Aij is 0, then you remove this site. If it's 1, then you don't remove the site. And then your stabilizers are x's along 2 sites that are next to each other along the x direction, but they could also jump over. And similarly for z, so like if for these two, for example, there's a gauge generator that sort of skips this missing site. And the reason to do this is that now if you have a logical operator, say on this row, versus a logical operator on this, on this column versus a logical operator on this column, they're no longer related to each other, and they act in different ways in the code space. So, and what ends up happening is that your total number of logical qubits, K, goes as the rank of this binary matrix A, and you can find some family of binary matrices that's, as you take the dimension to infinity, the rank scales as L, and the distance and n also scale in the same way as before. So this Bravyi Bacon-Shor code, which I'm just going to call the BBS code, now has parameters KD. The product scales as L squared, which is upper bounded by L squared. So now it saturates this bound. So this can store more and store information more efficiently than just the Bacon-Shor code. So let's apply fractalization to this. So sort of each site that was missing in the 2D BBS code, now when you fractalize it, this corresponds to a whole line. So this whole line of sites is missing in the fractal Bacon-Shor code. So just to show you what things look like, if you look at the logical operator, it used to be a fractal within this plane. Now it's just a fractal, but like some lines are missing. So it's just a fractal, but some lines are just gone. And like in the 2D Bravyi-Bacon-Shor code, logical operators on different planes are now independent. So your total number of logical qubits, K, goes as L times rank of A, which you can find some family of matrices that's such that K scales with L squared up from L. So the fractal BBS code now has these parameters. NKD is L cubed, L squared, and then distance is still L to some power eta. And this is our 3D bound. So if we look at this, we now have K square root of D is equal to L to the 2 plus eta over 2, which is around 2.5 to 2.79, which is closer to saturating the bound, but not quite yet. So to improve this even further, what we can consider is generalization from Z2 to ZP. So we replace X and Z's with ZP clock operators. So XZ now satisfy this commutation relation. And the reason to do this is that the fractals that are now generated by sort of ZP LCA rules, which for any prime P are still fractals. And this tends to increase the weight of bare logical operators, and the fractals will have larger Hausdorff dimension for larger p. So for example, f of x is equal to 1 plus x. This is our Sierpinski triangle. For p equals 2, it generates the Sierpinski triangle, which had fractal dimension 1.58. If we increase p to 3, it now generates this sort of Z3 generalization of the Sierpinski triangle. Fractal dimension is 1.63. You increase p to 5, fractal dimension increases even more, it becomes some other fractal, p equals 6. Some other fractal dimension increases even more. And so this fractal dimension, or Hausdorff dimension, it has this exact form. And in the limit where p goes to infinity, this approaches 2. And this was actually used by Yoshida to sort of saturate an information storage bound in classical spin systems. So our conjecture is that in the p goes to infinity limit, so the dimension of the bare logical operators, the weight of the bare logical operators will approach 2. But our conjecture is that the dressed logical operator, the minimum dressed logical operator, also approaches, also scales as L to the eta, where eta approaches 2 in this p goes to infinity limit. And like I said, it's very difficult to prove anything about this power eta because it involves some minimization over all these dressed logical operators, which can be quite, which is quite difficult. In this case, then the NKD parameters now are L cubed, L squared, and then the distance now goes as L to the eta, which goes to 2 as p goes to infinity under our conjecture. Now distance saturates the distance bound, and this combination k squared of d now scales as L to the cubed, which saturates this other bound as well. So this fractal BBS subsystem code, we conjecture asymptotically saturates this bound. And one way to see this is that, as well as generalized to higher dimension, is recall that we can always view fractalization as, from d to d plus m dimensions, as start this 3-step process. I mentioned this way earlier in the talk. So we start with some layered system, we relabel the gauge generators, and then we perform some non-local unitary transformation. So step 1, if you start off with an NKD code, so this would be the Bravyi-Bacon-Shor code, you put it layered, starting with the layered system in d plus m dimensions. This just modifies m and n and k to be L to the m and times n and L to the m times k. Step 2, you just relabel gauge generators. This doesn't affect NKD at all. And then finally, there's some non-local unitary transformation, and this doesn't affect n or k, but it will affect d, and in this case, it sends d from L to the eta. And you can just see this 3-step process. So you start off with BBS code, L squared LL, layered BBS code for going in 3 dimensions. So this is for m equals 1. This becomes L cubed, this becomes L squared, this doesn't change. And then finally, there's some unitary transformation connecting this layered to this fractal BBS, and that turns distance from L to L to the eta. Using m greater than 1, you can generalize this to higher dimensions. So the 2 plus m dimensional fractal BBS code has parameters L to the 2 plus m, L to the 1 plus m, and distance L to the eta, where now eta is some number between 1 and 1 plus m. And this will saturate the bound if eta approaches 1 to the m. So if you find some fractals and maybe you take p goes to infinity like we did before, then you can find some family of codes that saturates this bound in any dimension. Okay, that's it for my talk, but let me just mention some questions. Other applications, you give me any model that's sort of CSS type, it has only X's or C terms. I can just write it down, go through Fractalization cookbook, gives you a higher dimensional model. Maybe some more interesting models can be found in this way. Some ideas, for example, you can start with some D-dimensional toric code. This gives you family of d plus m dimensional type 2 fracton phases, for example, like we could fractalize this loop-only toric code to end up with some higher dimensional fracton model with loop-like fractonic excitations. You can also fractalize fracton phases. So like this x cube model, what happens if you fractalize that? You get a higher dimensional fractal version of x cube. Lots of stuff to explore. I can also generalize to other cellular automata, like is it possible to do like higher order cellular automata, or maybe even nonlinear? Well, these are all that could be, yeah. These are open questions, and there's also lots of questions regarding sort of the properties of this fractal Bravyi-Bacon-Shor code as a code, which I haven't really delved into. Thank you.
Thanks, Trithep. Let me play some applause. 1 second. Okay. Any questions? I think we have plenty of time. I think the audience can ask questions in the Q&A. Is that right?
Yeah, there's a question from the audience, Austin. You can talk.
Yeah, can I let him speak?
Mm-hmm.
I'm unmuted. Right. Yeah, so I guess you talked about applying this fractalization to these one-dimensional SPT phases in order to get these subsystem SPT phases.
Yeah.
I was wondering if you had any comment about like how the symmetry fractionalization looks in the fractalized model.
Yeah, so I mean, in the example here, I don't know the answer more generally, but I know for the case of here. So in this case, the symmetry fractionalizes sort of on the edge as sort of these two sort of anti-commute at the edge. If you look at how these fractal subsystems symmetries in this model, how the symmetry fractionalizes. So if you cut an edge along an edge vertically like this, and then you have two symmetries that sort of terminate at the edge. So there's this blue one here, and then there's this red one here. So sort of this blue one localized on the edge will anti-commute with this red one that's localized on this side, but not it will commute with everything else that sort of is somewhere else. So it's, in this sense, it's like exactly the same as for basically if you had stacks of, or like layers of 1D SPTs, sort of the symmetry fractionalization is local within each chain. Yeah, but I mean, there are also more complicated fractal SPTs. Like given this symmetry, there are more complicated phases, but I'm not sure. I mean, that's a good question. I'm not sure how I would obtain those as fractalization of some 1D SPT. I could probably write it as a fractalization of some more complicated 1D SPT. Maybe you have to like, it would be like a Z2 to the 4th SPT, and then you'd have some unit cells, and I could probably do that.
Mm-hmm. Sure. Yeah, I guess maybe to follow up on it, I was sort of thinking about how if you have this like finite string of symmetry operators, the symmetry is fractionalized at each ends, but collectively about the two ends, they form a linear representation of the symmetry group.
Yes.
And I was wondering if like something happened here, it's sort of like the three corners of like a membrane operator that I may apply.
Yeah. So if you just apply this triangle operator, for example, this will have something on this end, and on this end. But then but sort of as a whole, everything has to work out. But if you just localize it to one of these corners, then you can have some projective representation.
Sure. Thank you.
Thanks.
Any more questions?
I have a question.
Sure.
I think you may have answered it on your last slide on your Outlook, but yeah, so you used a product of two 1D cellular automata when doing the 2D case. Can you use a 2D cellular automata? And if not,
yes.
is it obvious what doesn't work, or?
So, right, so let me go to the definition of fractalization. So it goes from D to D plus M dimensions, right? So this is the most general case. So M is the dimension of the cellular automaton. So if you use a two-dimensional cellular automaton, it'll go from D to D plus 2 dimensions. You always need D different LCA rules, but the dimension of the LCA rules determines what your M is.
I see.
Yeah.
Yeah.
So
Okay.
yeah. So if I wanted to create a 4-dimensional fractal BBS code, I would need to use two-dimensional LCA rules.
So then what did you mean in your Outlook when you mentioned higher order cellular automata? What do you mean here by order?
Oh, higher order. So everything, so like the state at time t can depend on time t minus 1 and time t minus 2.
Okay.
And the reason that's sort of interest is because Haas code, you can sort of move around the sites and do some transformations so that you can write it as sort of in the same form as Yoshida's fractal spin liquids, whatever that is. But it's not a first order cellular automaton, it's second order. So
I see.
right. So if we could, right, so if we extend this to second order cellular automata, then Haas code would also be captured by this.
Thanks.
Thanks.
I have a possibly related question. So your construction of fractalization is CSS-ness preserving.
Yes.
And that's presumably from the classical origin of linear cellular automata.
Yes.
But can you envision cellular automata that kind of take input from both the X and the Z part and kind of mix it? And then have you considered that? Would that have interesting examples?
I've not considered that, but that is a very good question, and it might, yeah. I haven't considered that. Yeah, it might be a way to extend this beyond just CSS codes.
Okay, good. But maybe most interesting examples are of CSS type.
Well, the examples we know of are of CSS type. There could be more interesting examples we don't know yet.
Okay.
Great. I think we still have time for any more questions if someone else wants to ask something.
Hello?
Yeah, we can hear you now.
Oh, okay. I was wondering, like, does it extend to like beyond stabilizer? Say if I take like Kitaev's honeycomb model or something, like, will that still work?
Kitaev's honeycomb is not CSS, so
Right.
I
So
wouldn't be able to
you're
apply.
saying you have to start with CSS only, or?
Well, it has to be like only have X and Z types. It doesn't have to be a CSS code. Like, doesn't have to commute. Like the Bacon-Shor code, right? The gauge generators don't commute. But it needs, every operator needs to be of only X or only Z type.
I see.
Actually,
so the honeycomb wouldn't work.
Yeah.
And what's the obstruction, or what goes wrong when you try to do that?
So sort of everything, like X and Z's are treated differently, in such a way that it preserves the commutation relation. And if there's some operator that has like both X's and Z's, then there's no way to do that in a way that sort of preserves locality. I'm not sure if there's a better way to explain it.
I see.
Okay, I think we still have time if there is any more questions. But probably everyone who wants to ask a question is asked at this point. Maybe I could just follow up on Nat's question. You could obviously take the y term in honeycomb model and you could apply the fractalization to the xx and the zz part, but you're saying doing the obvious thing there somehow doesn't work.
You could. I'd have to see what comes out, see if it makes sense.
But yeah, maybe you lose some of the other properties that we have for the CSS fractalization.
Yeah, you might. But yeah, that's another good question.
Okay. If there's no further questions, I think we can thank Trithep again, and David can get set up.